The demonstration corner. Today we'll be talking about the THW-L1 for measuring thermal conductivity, thermal diffusivity, and specific heat for liquids and phase change materials. As tradition, before we do that, we'll do a little turn of the camera and show you all the instruments that are available in our demonstration corner for demonstrations like this, training, after-sales support. We invite you to ask for a one-on-one demonstration of any of the equipment you see. So, turning the camera to the left, we have our MP2, which is basically what we would call the portable version of the measurement platform series that has a range of primary methods for measuring thermal conductivity, transient plane source for solids, transient hot wire for liquids, and transient line source for soil and polymer. Then we have our baby brother to the heat flow meter series, our HFM25 for measuring small format insulation, and then the THW-L1, which we'll talk about. Turning to my left is the new MPV, which we'll be talking more about next week. We're doing a demonstration series on that. The MPV standing for versatility, combining multiple methods for intelligent thermal conductivity. And then our marquee, the industry leader in transient versatility for measuring thermal conductivity, diffusivity, and specific heat across multiple methods. The MP1 being the highest level measurement platform we have, which combines the ability for multiple methods as well as a switch and intelligent software to connect those all together and increase volume and ease of measurement. And then we have our guarded heat flow meter following ASTM E1530 for measuring complex materials, complex meaning heterogeneous and or non-repeating layers. That's relatively important because this measures a one-directional thermal resistance, and anything you put between the plates you're going to measure resistance of. So it doesn't suffer from any theoretical assumptions that are indicative in direct transient methods. So I invite you to learn more about that. That temperature range on this device is -20 to 310 Celsius from a plate temperature. So this is our steady state device. And then we have our heat flow meter, one of a few. This is our HFM100. This has a plate temperature of -20 to 75 Celsius, and this is for measuring large format insulation and construction materials. This one has an inside dimension of 300 by 300 and up to 100 millimeters thick. The thickness can vary, of course. We have a high temperature version of this that has a plate temperature of -30 to 110 Celsius and the exact same internal dimensions. And then we have the HFM50, which is 200 by 200 millimeters and up to 50 millimeters thick. Right now we're actually measuring, I would open the door and show you, but right now we're measuring specific heat. So there is, to expand the ranges on the heat flow meter, we can go up to 2.5 watts per meter Kelvin with extended range thermal conductivity kit, and then we have a specific heat module. So there's actually a measurement being done right here, measuring the specific heat of the sample inside it. And once you know conductivity and specific heat, you can calculate thermal diffusivity as well. So coming back to the transient hot wire, THW-L1, this follows ASTM 7896 for measuring, again, thermal conductivity, thermal diffusivity, and volumetric specific heat for liquids and phase change materials. We do have specific accessories for measuring phase change materials, and that's a cell that accommodates change in volume. That's really key to keep the phase change material in contact with the sensor. But today we're going to just talk generally about the THW-L1. So this unit, as well as our MP1 series, we've got a proprietary heating and cooling device which allows us to integrate heat along with the controller. So inside this one box is both the data acquisition as well as heating and controlling temperature. Now, of course, you can make measurements at room temperature, but you can also make measurements at room temperature as well as over a temperature range. This L1 as it is here is our basic unit. This will go from 10 degrees to 200 degrees Celsius and up to a back pressure of 20 bar. We have extended range options that'll go down to minus 45 Celsius and even minus 160 Celsius up to 300 Celsius. And that extended range also allows for back pressure up to 35 bar. Why is back pressure important? Is because it allows you to test past boiling points. That's key if you want to test water past its boiling point. The sample we're going to do a quick demonstration on today is ethylene glycol. Ethylene glycol has a boiling point around like 185, something like that, Celsius. If you wanted to test ethylene glycol to 200C, you would put through this connector a back pressure of maybe 10 psi, and that would allow you to test past its boiling point. This is our room temperature stand. This actually has a hexagonal shape to the bottom that allows us to position it on the bench and unlock it or unscrew it, loosen it. You can do that with a wrench. It's not tight right now because we don't have a sample loaded, but I can pull it out. We're going to just show you what it looks like. So this is our liquid cell. This is common stainless steel. We have, again, different accessory versions of our cell. One of them is observation, which is glass to allow you to look at if there's any phenomenon happening within your sample. The other one is a phase change cell that allows you to change, allows you to accommodate different changes in volume. And then there's a powder cell and variable density powder cell. So that holds about 20 milliliters of fluid. The sensor itself is a platinum wire suspended between two contact points. You can see our contact points here. So if you break a wire, you can just use the set screw and change the wire and start measuring again. I will hopefully be able to show you a little bit. We'll do our best. It's a really small diameter, but there is a wire suspended between those 2 points. So hopefully you can get a visualization of that. This, what's inside of here is a PT sensor for measuring temperature of the fluid. So in fact, we're measuring the exact temperature of the fluid. So when a measurement is done, we pass a current through that platinum wire between those two contact points. This is a 4-wire resistance read with a Wheatstone bridge, and we're looking at the change in resistance related to the heat of diffusion from the wire into the sample, and we get a temperature rise versus time slope, and from that we calculate thermal conductivity and diffusivity. Volumetric specific heat is auto-calculated, or if you input the densities, you get mass-based specific heat. So that's construction of the sensor as it is here. This one is good to 20 bar. There's slightly different construction for 35 bar, although it's all internal. You might not know it, but there's a couple variations of the sensor depending on temperature range and pressure. So we can put that aside, and we're going to load the sample. In this case, we're going to load ethylene glycol. It's about 20 milliliters. So I can't angle the cell or it will all just spill out, but you sort of have to get the idea that we're filling it to about top of the cell. And then we're going to insert the sensor into the cell and just turn it. We're not going to do high pressure with this in this demonstration, but if I was, I would put a back pressure on here depending on the temperature I'm going to and the boiling temperature of the sample. We're going to load this into our temperature platform. Before I switch to the software and show you what that looks like, just talk a little bit about what is the temperature platform. So this, as it is thermal electric chilled. So there's no external cooling. It's all internal cooling on this particular model that goes from 10 degrees to 200. The other models are 0 degrees to 300, minus 45 to 300, and minus 160 to 300. Those other three models have variations of liquid and/or liquid chiller, or variations of liquid nitrogen to cool them. But it's all in the same dimension of controller box. So what's really interesting about the way we control temperature that is common to our THW as well as our MP1 series temperature platforms is that it has integrated cooling and heating. So if we were to destruct this and show you a cross-section, you would see opposing temperatures. So that sensor is sitting inside of a heated well with a gap in spacing between the heated well and the cooling dimensions around it. And that allows us to precisely control temperature. So there's always cold and always heat opposing each other. So we get very good control of temperature. And it allows us to go from cold to hot without switching to different cooling and heating apparatuses. So that minus 45 to 300 Celsius that I was referring to, that's the sensor never leaves this port. That cooling is done within the device itself. There's some other makers of transient hot wire out there, a hot wire method that you have to sort of switch if you go below a certain temperature to another cooling device. We can set up one schedule because this is all integrated and allow us to do a full range of temperature depending on if it's cryogenic or subambient up to high temperature. So that's a big advantage of that. And of course, we get very good stability of temperature. So I'm going to switch to the software now. I'm just going to walk around the camera. I'm going to get a piece of paper towel first, actually, and share the screen. So here's my screen. Oh, that's the website, rather. And we're going to go to, this is what your screen looks like when you first load the L1. And as we can put in the username, I'll just put lab user, the name of the sample. So as part of our design of transient methods, we've integrated an approach to measurements, a selection of parameters, and it's what we call the I-transient, or intelligent transient. On the L1, we would refer to that as the, whenever we're talking about automation of parameters, I would refer to that as the I-THW, or the intelligent THW. When we're talking about the transient plane source, we would refer to that as the I-TPS, or the intelligent TPS. In the sense, we are leading the industry on development of parameters using an intelligence approach. And that's really important, because although you can still do manual, we want to keep that spirit of measurement to allow you to do manual manipulation, both selection of parameters and looking at and analyzing data. But using the 20 years experience we have in transient methods, we can develop very intelligent instruments that takes away the need to iterate through a measurement. So in our THW, one step, you can do this manually or as part of the schedule. I like to show from a manual point of view, because it gives you an idea of what I mean by added intelligence, is we can select detect power. So now that the sensor and sample are loaded inside the temperature platform, we can detect power, which goes out and does a very unique probing measurement and develops from a set of criteria from that sample, that unique sample. So we're not, we're doing this on the sample that we're actually going to analyze. It develops the power needed for that sample based off its thermal-physical properties, so its conductivity and diffusivity. So once that's done, that will populate the power required to meet certain criteria of measurement. Again, as part of the training, we explain those criteria and describe how you might do them manually if you choose to, but of course, you don't have to memorize that. The intelligence involved in the instrument allows you to automatically detect that. If you want to edit densities, here's where you can put in the multiple density of temperature points for your sample and load those as a cell. Rather, load those to the experiment you're going to run over temperature. We're not going to bother with that. So we'll save the power associated with that sample. So hit save. And here's where we can run a single measurement, which I'm going to do because it's kind of neat to show that you can run very easy measurements at the temperature that you're testing at. So we'll run this. And once we're done that, I'll demonstrate how to run a measurement with temperature. Now, ideally, you're waiting a few minutes before detect power and running a single measurement, because it does introduce a little bit of heat into the sample from that probing experiment. So typically, you'd want to wait maybe 5 minutes for that to dissipate. But again, you don't have to run this manual measurement. You could just go to the schedule, and it's already built in to detect power at each temperature. So there's the thermal conductivity and thermal diffusivity and volumetric specific heat associated with that very quick measurement of ethylene glycol at 21.1 degrees. Now, ideally, we're going to make a scheduled measurement of temperature. And so here's where we can add. We're going to do temperature steps. And let's do a start temperature of 10 degrees and an end temperature of 90 with 10 degree steps. And here's the name of our sample. We'll do 3 measurements at each temperature with a 10-minute delay. Auto power is enabled. So what that'll actually do, once I hit save, you'll see that schedule built. It will go to 10 degrees, detect power, wait for 10 minutes, because we want to have high accuracy values with no introduced drift from the detect power. And then it'll automatically make 3 measurements, then go to 20 degrees and repeat that process until it gets to 70 degrees, or 90 degrees, I'm sorry. And then when it's complete, it'll go back to 20 degrees. You can basically vary any one of these experiments to meet your needs. If you want it to go back to 0 degrees, or if you want it to stay at 90 so that you can review data, so you can vary that last step to be different. So we can press start, and what you'll see, oh, we want to save the experiment. That's the destination of the saved data. What you'll see on the screen, the Wattlow controller is the set temperature change to 10 degrees, and the cooling part of the temperature platform, the integrated temperature platform, will take over and drive the temperature to 10 degrees. So here's where you watch this, and you'll see experimental data. And if you want to review that with temperature, there's no data here, but this is what it would look like. So I opened up another copy of the software. We ran ethylene glycol. And here you can see the same experiment schedule that I just set up already run, and we can look at data just to show you what it looks like. That's 10 degrees, and it shows as good quality. That is a line-by-line assessment of the quality of the data. If it's poor, you'll have a different color. If it's average versus poor, you'll have a different color red with some suggestions on what to do. Maybe there's drift in the data, maybe you don't have enough temperature rise, so that's part of it. Yeah, so that is essentially a measurement set. And from this, you can generate reports to Excel and review your data fully. And at this point, we would just wait for the experiment to proceed through the different levels and wait for data to be complete. All right, that is the THW-L1 for liquids and phase change materials. And if you have any questions, we'd be happy to answer them, and or get in touch with us if you want a one-on-one demonstration, or if you'd like to evaluate your own sample with this method, we'd be happy to arrange that.